Alrighty, so you think you know about factorizing. Let's see. Here's a quadratic. We want to factorize it. Factorizing means putting it back into brackets. So we have two sets of brackets that are going to multiply out to give us this. It's the letter M, so it's going to be M and M. Now, the two numbers that go in here multiply together to give the n term, but add together to give the middle term. So 5 times 1 will give us 5, and 5 plus 1 will give us 6. So plus 5 in one, plus 1 in the other. It would be 5m plus m would be 6m, but 5 times 1 would be 5. So these are the factors that make up this quadratic. Now that one seems pretty straightforward. And you might even know how to do the ones when a is not equal to 1. So there's a number, a coefficient in front of the squared variable. So what about ones that are missing a term? Can you do those? Let's have a look. Alright, so in this one, the first thing you'll notice is that there's no middle term. We've got an m squared, we've got an n term like the c, but there's no value with just an m in it. Now let's take a step back and have a look at our special rules. One of the special rules is where we have a plus b and we're multiplying it by itself, a plus b. If we were to expand this out, we get a squared. Then we have a times b, so that's 1ab. We have b times a, that's 2, so plus 2ab. And then we have b times b, so b squared. When we look at this, it's the same as doing a plus b all squared. And these were called perfect squares. And instead of doing the maths and expanding it properly each time, we use this as a shortcut rule. So you can see it's got an a squared term and an a term. This one doesn't have a coefficient in front of an m. It's missing something. If you think back to these rules though, there was another one called difference of squares. And in the difference of squares it was a plus b in one bracket and a take b in the other bracket. When we expand this, a times a squared, a times negative b times a plus b times minus b squared. This term and this term cancel out, so negative BA and a plus BA would be 0, and you end up with a simplified version of a squared minus b squared. Again, it was called difference of squares. So this was our simplified rule. Now have a look at this, have a look at this. They're very similar. We have an a squared version here, and a negative in the middle, and a b squared being 9 squared. So we could write this as m squared minus 9 squared. Now you don't have to write the step, but I'm just showing it to you. Doesn't it look like that? So the b then is the 9, the a is the m. So we can rewrite it as these brackets with an m plus 9 and an m take 9. If you expand that, you'd have m squared. You'd have plus 9m minus 9m, so no m's. And plus 9 times minus 9 would be minus 81. So this is difference of squares. So you look for, the pattern you're looking for is something squared, a negative, and another perfect square. Let's have a look at another one. Alright, so you're looking at this and you're saying, no, this isn't right. We've got a squared minus b squared. And here, yep, I can see that one might be 8 squared, but what's this? Well, you know that 4 is a perfect square. So really what you could say is that this is 2e squared minus 8 squared. Because when we bring in the power into the brackets, everything inside gets squared. So that would be 2 squared, which would be 4, and e squared. So that is the same thing. And 8 squared is 64. In this instance, the a is 2e, and the b is 8. So in one bracket, we write 2e plus 8, and in the other bracket, we write 2e take 8. If we were to expand that, which you should always check, you're going to get 2e times 2e, which is 4e squared. You're going to get negative 8 times 2e, plus 8 times 2e, which all cancels out, and plus 8 times minus 8, which gets you to negative 64. One more? All right then. Well, this one's got you. It's got a letter as the second term, the minus, but don't let that stop you. 9 is a perfect square, so we may as well write 3 squared. We put the minus, and that's just f squared. If we look back down here to our root, the rule is a squared, so 3 squared. So 3 is going to go in the bracket on this side, a plus, it's f squared, so the b was there, so f, and on the other side, 3 minus f. To expand it, 3 times 3 is 9. We have negative 3f plus 3f, so the f's are gone, and then we have f times negative f, which is negative f squared. So it's a perfect square. Now you're probably thinking, what about if it's not a perfect squared number? Well, that brings in surds. I don't know if you've learnt surds yet, but I'll show you an example. So, a squared minus 2. Now, it almost looks right. It's got a squared variable, it's got the negative, but it's got number 2, and 2 is not a perfect square. But we could still use this concept. It's just going to bring in surds. So basically, what we have in the bracket is the square root of the number which is here. Now, when it was 64, the square root of that was 8. When it was 9, the square root of that is 3. So the square root of 2 is just square root 2. So we can still put in the bracket an a plus, and in this case, root 2, and an a take root 2. If we were to expand that, we would have a times a, which would be a squared. We would have negative root 2a plus root 2a, which would cancel out, and we would have root 2 times negative root 2. And remember, when you multiply a square root by itself, it cancels out the square root, and you would end up with negative 2. And that's just bringing in surds. So I'm not sure if you're up to that in your course, but that's what you could do. And this has been the difference of squares. So what you're looking for, always looking for, is a perfect square, a negative in the middle, and a perfect square on the other end. And you can take it back to brackets which look like this.